Hello everybody. Once again, this is Mr. Steele. I'm introducing you today to the final unit of study for this particular term. In today's lecture, we're going to introduce you to a new type of differentiation. Now let me point out to you that this doesn't mean we're going to learn some new derivative rule like we did where we, for instance, learned that the derivative of sine was cosine. And we're not going to learn that differentiation means something different. We're going to still be focusing on the idea of slope. We're really focusing on slope until, 2 lessons from now, when we look at a concept called related rates. For the moment, what we're going to do is we're going to learn a new technique to approach with different types of relations. So up to this point, we've actually, without really knowing it, focused on a single type of relation, the function, to differentiate, and always had that explicit connection between two variables. Today, we're going to have something slightly different. So to begin with, I'm going to start by introducing you to the idea of what we mean by this non-explicit curve, introduce you to how it differs from some sorts of differentiation we've done in the past, particularly variables where there's new variables in there. And then finally, we'll work through some examples, kind of going through all the different twists and things that we'll go through. I'm going to keep today's lecture as short as possible because I believe today is an advisory day, but again, it's August 4th for me, so it's a little bit hard to tell. And then basically we'll go through some examples and make sure you're ready to go. And then we'll pick up some of the greater nuances, some of the bigger wrinkles, and some of the applications of this technique of differentiation tomorrow when we hit the advanced lesson. So for today, strap in. We're going to focus in on these new type of differentiation. So to begin with, before we can really start and talk about this new type of differentiation, it's important to establish why we might need such a new type of differentiation. So what I'm going to do is I'm going to present to you two different relations. The first one is y equals 42 over x, and the second one is going to be 42 equals x times y. Now, bringing these two different relations up, when you look at them for the first time, obviously they look different. Like there's something that's different between the one on the left and the one on the right. But something that's really important to point out here is that these are actually describing the same set of points. In fact, were I to pull up Desmos, I'm not going to for time, but were I to pull up Desmos and put either one of those down, I would get the exact same graph. Like these describe the same relationship. But they're presented in very different ways. The one on the left we call explicit. Now explicit sometimes, in the lots of different ways. Explicit means like profane or vulgar. This isn't exactly that kind of explicit. In this case, we're talking about explicit because it's very clear and the meaning is very there. More importantly, mathematically, there is an explicit relationship between y and x. In particular, y is a function of x. So oftentimes explicit relations, always explicit relations between x and y, start with y equals, then there's some stuff, and x. So you could almost say y equals f of x is our presentation. So in fact, I probably should just write that now that I think about it. So y is a function of x. In other words, if you give, y as a function of x. So in other words, we're saying that y depends on x. Basically, if you give me the value of x, I can put it into this little machine over on the right side, and when it's done, it will spit out the value of y. There's no other ambiguity about it. In fact, that's oftentimes how this is described. You plug in x, stuff happens, and you get y. That's it. It spits it right out. Now, on the other hand, if we look at the second relation, again the same one, just a different presentation of it, this relation is what we're going to term implicit. And that word itself, implicit, probably sounds like the word imply. Like when you imply something, you try to subtly sneak it in there, try to keep it on the down low, and you try to hide it a little bit, you try to mask it a little bit more. We call this curve implicit because all the variables, or in our case we should say more than all the variables, both variables in question are mixed together. And by mixed, I just mean that they're not explicitly separated. So in other words, we don't have in this relation, or in this presentation of that relation, we don't have y equaling stuff with x. Like we have x and y both together on a single side, meaning that the relationship is a little more implied. We know, we've been trained to believe that there's a connection between x and y, but it's not explicitly given to us that way. So in other words here, if we're looking kind of parallel to the left side and everything, on the right, if you have that relation, you're going to have to plug in x, and then you're going to have to do a bunch of stuff and move some stuff, really. and then you're going to get to y, maybe. Like, in other words, it's possible you might not even be able to solve for y even at the end. Like, the relationship might be that difficult for us to actually work through. Might have to use advanced techniques or a graphing calculator to get there. So now, with that said, let me remind you that we've spent a good deal of time working with explicit relationships. In fact, every single function we've attacked in this course so far has been an explicitly defined curve. So today we're not going to focus on the explicit curves. We're going to focus on implicitly defined curves. And we'll talk about some ones that are really common to show up geometrically or graphically. And then later on we'll actually use this to apply to talk about all sorts of different things and to really analyze more realistic problems through a process called related rates. Before I leave you, just because I have fun with it and I'm disappointed that I don't get to teach this lesson, every year I like to leave something there to kind of help you with the vocabulary of explicit and implicit, even though I feel like they're probably words that you've heard before. And that is, I sought out during the summer a volunteer to help me with this. So I'm not sure which class he's going to be in, but I know he's in one of our classes. So this is what I would call an explicitly clear situation. So in this scenario, you can see Nathan in there. This is Nathan Kumar. All images of Nathan Kumar used with permission. In this picture, we have a poor innocent baby seal. More on that later. We also have Nathan standing over the seal with a large baseball bat, wearing seemingly a blood-proof coat, and he is saying the words, "I am clubbing this baby seal." This is what I would call an explicit scenario. We are clear on what is happening. Nathan is about to club this baby seal. Either that, or he's really confused about what it takes to make friends with small, cute, cuddly animals. We say this is explicit because there's no ambiguity, the relationship is clear. We know what's going to happen next. Nathan is going to take that bat, put it down, and our poor future math hero will be injured. On the other hand, an implied situation requires a little bit of work for that relation to get there. And naturally, as it will with differentiation, it requires a little bit more interpretation and a little bit more intensity. So in this case, same smile. But this time, it's not so clear what's happening. We no longer have the presence of a cute, cuddly baby seal over on the side. Nathan is still holding a cudgel, which is not ideal. But now he's not saying, "I am clubbing the seal." He's asking if we have any baby seals. And his shirt seemingly suggests potential violence upcoming because it says, "I club baby seals." Or if you're not into cards, you might say, "I clover baby seals," but whatever. So again, the one on the left, explicit, it's very clear what's happening. We can follow this thing through all the way. On the right, it takes a little bit more work to get the implication of what's happening here. Not that much work, because otherwise it wouldn't be funny, but a little bit of work. So again, our job here today, it's not going to be so simple as just to get y equals f of x. Instead, we're going to have some implied relationships for us to work through, and we're still going to try to figure out what their slopes are. So again, today's focus is going to be on the concept of implicit differentiation. And there's your quick little intro. Now with that said, before we start, I wanted to start with a problem that sometimes got stuck in the heads of my students when I first started teaching implicit differentiation. And that was a problem like this. We have a function y equals ax cubed plus bx plus c. And in this case, when you look, this is an explicit relation because y is a function of x. But in this case, people get confused a little bit because there's so many different variables. And yet, if I ask you to differentiate this function, you can probably very quickly come up with the fact, or the answer, that y prime is equal to 3ax squared plus b. And that's interesting to me. While it is absolutely correct, my question is, how do you get there so fast? How did you know that was what we were doing? And the reason is, we know that there's a really firm connection between x and y, that these two things are related to one another, because of the fact that we relate them with x being an independent variable and y being a dependent variable related to x. So in reality, what's actually happening here, but not necessarily being shown, is we're taking that original relationship that has many, many variables, and truthfully, we're making an assumption. We're assuming that we're differentiating this with respect to x, because what we're looking to find is some sort of slope expression within the xy plane. So in this case, what happens, if we kind of look at this individually, if we take the derivative with respect to x of y, we'll still be taking the derivative with respect to x of each of these other terms on the right side. But since they're all deemed to be related to x, we don't have to quite worry about it. On the right side, we differentiate with respect to x. X is our variable in question. So over here, we take that x cubed, and we treat that a as some sort of scalar. And instead, we do the derivative with respect to x of x cubed. On the next one, we do the same thing. We do b as a scalar, just kind of assume that's the way it's going, and then we take the derivative with respect to x of x. And then finally, c is just a constant, which means we're taking the derivative with respect to x of 1. So much ado about nothing on the other side. Obviously, we get exactly what we'd expected, 3ax cubed, or 3ax squared. Then we get b. Now in this case, and obviously we're going to get 0 over on the far right side, sorry. In this case, you might wonder why it is that we get that 1 if you're not thinking about this in terms of linear functions and slope. Well, look at it this way. If we take the derivative with respect to x of x, we get dx over dx. And dx over dx clearly goes to 1, divides itself out. So we get 3ax squared plus b. Now on the left side, if we take the derivative with respect to x of y, we get literally dy dx, which is literally that expression for slope. It's the tiny little change in y over the tiny little change in x. And we just know that we call that y prime as kind of a convenient shorthand. And there is our answer. So in other words, as we look at this, the reason we're able to differentiate it so fast, despite the presence of 3 extra variables that we hadn't seen before, is because we assume, rightly in fact I would say, we assume that we are differentiating at all times with respect to x. X is the variable in question, x is the independent one, and of course our assumption comes from the fact that we're used to dealing with slope geometrically and thinking about what it looks like on some graph, that we're trying to figure out the tiny little change in x and the tiny little change in y. So in a sense, keep this in mind as we go forward, because in truth what we're about to do is kind of the same thing. The difference is we're not going to be limited to just x's and y's on separate sides, and we're also not going to be limited to having functions that look like just y. We're actually going to have more complicated things. So with that said, let's jump on to the next page. And let's present to you the first implicit curve we want to differentiate. So consider this an example. It's going to be more of an intro. In fact, I'm not even going to put example. I'm just going to consider this like our intro. So once again, you'd be asked to differentiate. And what we're going to differentiate this time is a familiar relation. X squared plus y squared equals 9. So now out of curiosity, as I write x squared plus y squared equals 9 up there, I would hope that you recognize what shape this would produce if we were to graph this. Can anyone call it out for me really fast? That's right. It's a circle. I love doing that. I don't know why. This is a circle. In fact, this is a circle centered at the origin. Not my best circle, whatever. And it has a radius of 3. So in other words, what we're trying to do in this situation is we want to figure out what is the slope on this circle at any point x comma y that satisfies this equation. Now, if you've done a bunch of research with circles before, you might have realized that there is a way that we could get this relationship really quickly. There's actually a fast way based on the x and y coordinates that has to do with what happens if you draw a radius and then you draw a line tangent to that radius. Like if you remember, these two things are perpendicular. So there's actually a way to get there that I'm not going to use for the moment, but I will point out that it is out there in case that interests you. Instead, I want to investigate what it is that we do when we have a relationship where x and y are each presented implicitly. Like this has x and y somehow together, but they're on the same side and we don't have y as an explicit function of x. So again, consider this kind of your intro, and then we'll do real examples with the plan and stuff in just a second. So here's where I want to begin this kind of investigation of what we're going to do. I'm going to differentiate with respect to x this entire equation. In fact, I'm going to use hard brackets just so it feels more official. So we're differentiating this entire thing with respect to x. So let's write out what this would look like a little more carefully. This would be the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And it's all equal to the derivative with respect to x of 9. And so there is the derivative that we're looking for. We want to compute and figure out what this ends up being, with our goal being to find an expression for dy dx. That's our goal. So in looking here, I see that there are two different pieces out of these three that are in here that are really easy to compute. The derivative with respect to x of x squared is just 2x. Nothing's changed there, we know that relationship. Second, over on the right side of the equation, the derivative with respect to x of 9 is just the derivative of a constant, which is like the slope of a horizontal line, which you should know, of course, is 0. So those two pieces come out perfectly fine because we're just differentiating with respect to x, and we have another function or another expression that is a function of x. Our problem, of course, isn't that. Our problem is naturally this. What in the heck do we do with the derivative with respect to x of y squared? That is a total mess for us to deal with because there's no x in our expression. So you might expect that we need something different to kind of work our way through this particular problem. And you'd more or less be right. So what I'm going to do is I'm going to do a little math soliloquy. I like to say that phrase. And what we're going to do is we're going to investigate what it would take to differentiate an expression like y squared. So there's going to be our kind of attempt, or it's going to be how we tackle this situation. So here's my thought. We want to attempt to differentiate y squared. Well, my thought here is that even if it's not a function, like a one-to-one function in the traditional sense, we always assume in these situations that y and f or x are connected, that there's some relationship that takes x and turns it into y. Like we do something to x and then it spits out y. So for the moment, what we're going to do here, for the sake of simplicity and clarity, we're going to assume that y is directly related to x. We just can't see it. It's on some other plane. It requires some special mathematical universal knowledge that we just lack at this moment. But y has some connection to x. With that said, what that does is it transforms our expression from being the derivative with respect to x of y squared into the derivative with respect to x of f of x squared. Now that's not actually that difficult to differentiate. In fact, this is just a chain rule problem. All we have to do is focus on the derivative of the outside and the derivative inside and work our way through all the individual pieces. So in fact, let's do that. Let's consider our outside function to be something and our inside function, which I'm going to call u, to be something else. So in here, our outside function, or our inside function, I think pretty clearly is the thing in the parentheses. I'm going to call that f of x. Now, of course, someone might point out that that's the same thing as y, and that's true, but for the moment, we can just kind of set that aside. We'll come back to that. That does mean then that the outside function amounts to u squared. Now, to use the chain rule, of course, we differentiate the outside, and we differentiate u, or the inside. Derivative of the outside is 2u. The derivative of the inside is f prime of x. Bringing all these pieces together, that would tell us that the derivative with respect to x of f of x squared is going to be equal to 2u, but hey, take a look, we'll write it here once, what the heck, 2u times u prime. And finally, we have that u is equal to f of x. So this will give us 2f of x times f prime of x. Now that's all well and good, and I'm sure you're thrilled to see that. So I'm just moving it up a little bit to make sure I don't hit my own head. So that's all well and good, but here's the one thing that we're missing. We made up that relationship, f of y equals f of x. So in here, it'd be better not to use this f of x that we created to fill into the situation. It'd be better to use the name y. So in other words, making a back substitution with the fact that y equals f of x, we can write this derivative as 2y times f prime of x. But here's one more thing. Although f prime of x is itself f prime of x, again, we made that up. But notice, if we differentiate y equals f of x, we get that y prime equals f prime of x. So why not substitute this in and just call it y prime? Because the nice thing here is that this has just given us the answer to the question we were looking for. This is the derivative with respect to x of y squared. The derivative of y squared is 2y, which is exactly what we should expect, since the derivative of x squared is 2x. But because of that connection between y and x, that connection we called f of x, y equals f of x just for simplicity, we have 2y times y prime to satisfy the chain rule. That's really all there is to it. And with that in place, I'll just use a different color. Once I have that in place, we can now finish out our derivative. We end up with 2y times y prime. So there is our implicit technique, which again, I'll show you in a second. We'll go through some examples. I think it'll be okay. For the moment, it's there. Now let me make one little extra caveat. Although we're calling that f prime of x part y prime, some places we'll call it dy dx. That's absolutely accurate. In fact, that's what we're trying to find. But for the sake of simplicity of computation, I prefer to call that y prime. We're establishing what variable we're differentiating with respect to every time we write ddx, so I'm not worried about that. Instead, I'm just going to focus on calling it y prime. And you'll notice that in all of my work. I'll switch it back at the very end. Now with that said, to finish out this problem, our goal is to find dy dx, that expression for the slope at any point on this circle, x squared plus y squared equals 9. To do that, we just want to solve for y prime. We want to get that alone. So I'm going to subtract 2x from both sides. That will get me on the left 2y times y prime is equal to negative 2x. And last but not least, if we want to get y prime by itself, we just divide by the other stuff. And that will lead us to our derivative y prime, which we prefer to call dy dx. It looks a little more formal, establishes that connection between y and x. And then finally, that's equal to, if we divide the 2's, we're going to get negative x over y. And there, my friends, is our implicit derivative. And in here, it might feel weird to have a y in your derivative, but keep in mind we started with a relationship that implicitly connected x and y. It was just presented without having y explicitly as a function of x. I think it's appropriate to end up with a derivative dy dx that has an implicit connection between x and y. So at this point, we've actually successfully differentiated implicitly for the first time. And that's a pretty big move. But again, obviously there's a little bit more to it, and that was pretty fast, but we'll get there in just a second. Now, before we start refining the technique further and making it a little bit clearer and working on plans and everything and seeing all sorts of examples, I want to convince you that this actually gets us the exact same answer it would if we had the explicit version of this same relation. So to help me with that, I've taken the work we just did implicitly in differentiating this circle with radius 3 centered at the origin, and I want to go through and differentiate it explicitly instead to show you that these two things actually end up the same. Otherwise, if we're getting two different expressions, it can't possibly be correct. One would have to be wrong. So what I mean in order to do that is I first need to understand exactly how I would get an explicit relation out of this. Specifically, if I subtracted x squared from both sides, I'd have the relation y squared equals 9 minus x squared. And then from there, if we square root both sides, we'd end up with y being equal to plus or minus the square root of 9 minus x squared. So although this is not a function because of the fact that it's not one-to-one, like in fact, of course, just draw a circle, you can see it's not one-to-one, it fails the vertical line test. But because that plus or minus isn't a function, but this is still explicitly defined, basically you put something in for x, and then once you finish your computation, you'll end up with your y value, or in this case, values right afterwards. So from there, what I'm going to do is I'm going to differentiate this expression. So if this is the relation that we have, let's go attack it. So let's differentiate it with respect to x. Now on the left side, the derivative with respect to x of y is just simply what we'd expect. We get either 1 y prime, or we could just think about it as dy dx, or y prime. So I'm just going to call it y prime for now. On the right side, this also requires the chain rule. We've seen a lot of the chain rule. And in this case, I don't want to spend forever doing the explicit work on the chain rule, but let me point out that my outside, if I were to do the chain rule, the outside would be plus or minus the square root of u, and the inside would be the 9 minus x squared. Using that relationship, you can hopefully catch that this becomes plus or minus 1 over square root of u times the derivative of u, which is negative 2x. Now from here, rewriting this a little bit and just kind of maneuvering some stuff around, and again, trust me that this will work out, I'm going to rewrite this as negative 2x over plus or minus the square root. Oh, sorry, I forgot a 2, didn't I? My bad. Me malo. I need that 2 in there. Plus or minus 2 square root of 9 minus x squared. So at this moment, you can see very quickly that the 2's divide away, and it's tempting to try to condense that negative sign into the plus or minus, but bear with me for a moment. What we've just written is that y prime is equal to negative x divided by plus or minus the square root of 9 minus x squared. And if you're like me, the first time I did this demonstration in class, just kind of off the top of my head, hoping that it would work out, you might look at this and start to feel like, oh shoot, it's different. Oh shoot, what do I do? What did I do wrong? What was my mistake? But in fact, take a look at this. Negative x over plus or minus the square root of 9 minus x squared. Plus or minus the square root of 9 minus x squared gives me kind of that weird feeling of deja vu. And that's because deja vu didn't work. We just saw that expression. We were solving for y and we got that y is equal to plus or minus the square root of 9 minus x squared. In other words, this denominator is actually equal to y. And why that's so important is because it means our derivative is negative x over y. So these two expressions are in fact the exact same thing. They're twinsies, like they are identical, because of course they are. We're describing the exact same relation here as we are here. Implicit differentiation just allowed us to avoid rewriting this in explicit form. Gave us a nice, convenient, and really clean, I might add, derivative expression, whereas this one, that's kind of messy. So in fact, that might not even be the best form for us to work through. So what you're seeing is, of course, implicit and explicit are completely identical. They're equal to one another. It's just the process through which we do them is different because the presentation of the function was different as well. So as a heads up, yes, there are some situations where you could actually find the derivative using explicit differentiation, like our old school techniques, but know that I'm going to give you functions that don't actually allow you to solve for y in this way. And the reason why is because, of course, I want to test you on implicit differentiation. It's an important skill and it's a valuable skill. And again, we'll take a couple days to really see the payoff, but it will be there. So there you've at least seen that implicit and explicit are exactly the same. And with that said, let's jump in and actually do some real problems here and start formalizing this technique. So to begin with, let's focus on a pretty basic first problem, and then we'll kind of up the ante as we go forward. So first, what I want us to do is I want us to compute dy dx for 2y equals x cubed plus 5y to the fifth minus 1. So this implicit relationship is kind of out there. It's very weird, and in fact, I graphed it on Desmos earlier. It's not even a one-to-one expression either. So basically, it's not our best option, or it's not our favorite option, but we have this new technique that we want to go through. So I want us to actually go through and see what it looks like to implicitly differentiate. I will, though, as mentioned earlier, include a plan. So first, the first step we're going to take, beyond rewriting this expression, is we're going to differentiate. And when we do that, we can't simply just say differentiate because there's this xy connection that's in there in the chain rule. So what we're going to do is we're going to differentiate both sides with respect to x. And again, this feels a little bit weird. You might ask why it is we choose to do x as the special variable, but the reason is simply that we consider x to be the independent variable. And in our xy plane, we have x as the horizontal change. And we want to find a vertical over horizontal change. So now when we go to differentiate both sides in here, there's going to be two different approaches that we'll take. First, if the expression has x in it, that's just going to be normal differentiation. And the reason, of course, is that when you differentiate an x function with respect to x, you get the derivative you expect. The big change for us is that if there's a y in that expression we differentiate, as in we're differentiating like y squared with respect to x, then that means we're going to have to do the normal differentiation as well. But then we'll have to multiply times y prime, or dy dx if you prefer to be a little bit more stuffy and formal. So in here, let's take a look at what that looks like. So for the sake of simplicity, I'm going to copy my expression one more time, and then I'm going to differentiate the entire thing with respect to x. If you're wondering, yes, I really do want to see that d dx in front of it. I think that's an important place to establish what we're differentiating with respect to, which will matter a lot, give it 2 days. So in here, just kind of looking at our pieces, I'm just going to be super formal. I'm going to have d dx of 2y on the left. On the right, I'll have d dx of x cubed plus d dx of 5y to the fifth, and then plus d dx of negative 1. Now again, I think this will be one of those steps that you probably won't do when you're doing this yourself, but I'm trying to be explicit here, especially in my absence. So in looking at our expressions, again, doing the easy ones first, derivative with respect to x of x cubed is just 3x squared, and the derivative with respect to x of a constant like negative 1 is 0. Our big problem is handling the other two that have y's in them. But of course we know what to do here. So think about these functions as just in terms of x. If we had the derivative of 2x, our derivative would just be 2. But there was a y in there, so we have to use the chain rule and multiply by y prime. Likewise, if this was 5x to the fifth, our derivative would be 25x to the fourth. So our derivative here is going to be 25y to the fourth. But because we differentiated the y, there's that chain rule connection, so we multiply by y prime. That's it. That is the only part here that's new. This is the only real calculus we're doing in this problem. We just have to multiply by y prime when we literally differentiate a y function or expression. So with that in there, and with that in place, we've done all the heavy lifting. Our next move is going to be to start to do some algebra. In fact, you were preparing for this when you took like Math 1 or maybe even in elementary school. In this case, what we're going to do is we're going to kind of pull a Pokemon move. We're going to collect them all. And in particular, what I mean is we're going to collect all y prime terms on one side. And so what that means is, in a sense, we're trying to get all the y primes together so that we can eventually differentiate them out, or to GCF them out. We want to eventually factor them out so we can solve for y prime. And with them all kind of messy all over the place, it's hard to get there. So in this case, we got a couple options. I'm going to, in this case, subtract 25y to the fourth y prime from both sides. Again, there's a couple different ways we could do it, but I'm trying to pick one out. When we do, what we're left with on the left is 2y prime minus 25y to the fourth y prime, whereas on the right, all we have is 3x squared. So there is all our work. We've got all the y primes on a single side. From here, again, no calculus, very simple algebraic move. We're going to GCF out, as in greatest common factor, or find the GCF of our expression, and in this case, we've made our expression y prime. Y prime is the GCF of right here and right here. And even if there was more, we really only care about getting y prime by itself. So in this move, it's actually really simple. Although it's kind of awkward to have that like prime symbol on there. We get y prime times the quantity, 2 minus 25 y to the fourth. And all of that is equal to 3x squared. Now the final step is probably the easiest step of the entire process. Our final step is to solve for y prime. And if you've done this process correctly, solving for y prime is always going to be dividing. You're basically always going to divide. I guess technically you can multiply. You'll do something to get rid of that extra factor that's being multiplied times y prime. So in our case, I'm going to divide both sides. Wow, those are some of the straightest lines I've ever drawn. We were going to divide by 2 minus 25y to the fourth. When we do, we end up with y prime alone on the left, which we know is technically dy dx, just a slightly better form of it. And that's equal to 3x squared over 2 minus 25y to the fourth. And there is our implicit derivative. Now with that said, before we move forward, let me point out that this is actually just one of two very acceptable forms that you could have taken for this particular derivative. The reason I bring that up is that when I made my choice right here to subtract 25y to the fourth y prime from both sides, I actually made one of two different possible choices. I could have also instead subtracted 3x squared from both sides and subtracted 2y prime from both sides. Had I done that, I would have gotten the same answer, but it would have been presented differently. That answer would have been negative 3x squared over 25y to the fourth minus 2. So if you were working ahead a little bit and you got this expression and started to feel all glum and dejected, like, oh man, I did it wrong. That's my Eeyore impression, by the way. If you did that, you're actually totally correct. That is an absolutely acceptable final answer, and it's really just a mathematician's artistic touch that decides whether or not you should go subtract one way or another. So don't get discouraged. Like if you're looking at the homework or the video solutions, I try to always make a note of it, but keep in mind that again, it could just be a negative sign error or negative sign difference. Like these two things are the same if you just multiply it up and down by -1. So with that said, that is our process for implicit differentiation. It's not particularly crazy. Like it's really only that first step in getting used to the y derivative times y prime. But once you've got it, you'll be in really great shape. Now, with that said, I think that it's a really good time before we go into more advanced stuff to let you just do this once. So I'm going to take a few moments, or give you a few moments, or ask you to have a few moments to work through and differentiate implicitly on your own. And I'm giving you, in this case, a slightly more complicated expression here. In this case, it's 11y squared minus 13 plus 5x equals x cubed plus 2 cosine of y. So I want you to compute dy dx for me using implicit differentiation, just to get a feel for where you're at here and to give you a chance to ask some questions if you need to. So if you haven't already, please pause the video now. Or since that's the first time I said those words, please pause the video now. Okay, with that said, hopefully you've paused that video and had a chance to work through that try at an appropriate time. With that in place, let's jump in here for a second and look at the answer to this question. Guess I can paste in our step-by-step thing, even though I all did it in purple in this case. So in here, when you're differentiating, of course, we were differentiating with respect to x. The pieces that we had to go through, we had 2 that involved y, 11 halves y squared, and the 2 cosine of y. but otherwise they were just some normal x expressions. So in my work here, you can clearly see first that I differentiated with respect to x. That produced the y primes on both the first and the final terms. And then from there, I chose to subtract 5 and add 2 sine of y prime to both sides to make things clear. So in a sense, that was my work in red. After that, my job was to GCF out y prime. So that was my work right there. Fixing the colors so that way they match a little bit better. So I GCF'd out y prime from 11y plus 2 sine of y. And then, of course, I divided both sides, and that gave me the answer that I was looking for. It turns out our derivative here, dy dx, is 3x squared minus 5 over 11y plus 2 sine of y. Now, as a heads up, there are a couple, as we've mentioned before, there are 2 different ways you could have written this. I'm not a fan of this second version, but just in case you may have done it yourself, let me just point out to you that this would have been your alternate answer. So just keep in mind, if you got something that looks more like that, or negative 11y minus 2 sine of y, totally fine. You just wrote it in a slightly different form. But in any event, that is kind of your classic implicit differentiation kind of problem. And again, this one might have thrown you a little bit, that derivative of 2 cosine of y, but the derivative of 2 cosine is negative 2 sine, and then we multiply that whole thing by y prime. So that y prime's not stuck inside the argument, it's outside of the argument too. So hopefully that was informative. Let's jump into a problem that starts to up the ante a little bit and gets a little bit more difficult. So in here, we're going to attempt our next problem using implicit differentiation. And again, I'm going to put my little plan up there at the top. Let me point out, though, as we look at this for the first time, that at first glance, this might not actually seem like it's very difficult. It looks pretty much the same as what we saw earlier. Like we've got x's and y's together. Here's the thing, though. 3y to the 7th, I bet you can do that one by now. Sine of y, after that last problem, you're probably okay too. What makes this difficult is the presence of that term, x to the 5th y squared, specifically because that term in there is going to require us to use the product rule, because we really do have 2 different pieces being multiplied. We have x to the 5th as one sort of function multiplied times another, which is y squared. So in this case, we've got to be especially careful when we attack that piece. And I bring this up and include this explicitly as an example, explicitly in the implicit lesson, because people tend to have trouble with the product rule in these situations. They lose track of where the y primes go, or they just skip the product rule altogether. It's an essential part, and you can guarantee you're going to run into this again. So in our situation here, let me first make a quick copy so that we can actually attack this. So there is our relationship as with before. I'm going to differentiate it with respect to x. Now as we go to attack, let's do the ones that are cleanest here. The derivative with respect to x of 3y to the 7th. And again, you want to get more comfortable, make this mechanical work faster. So 3x to the 7th, the derivative would be 21x to the 6th. So our derivative here is going to be 21y to the 6th, but because we differentiated a y, we need to multiply by y prime. The next one, we'll deal with that in a second. Again, do something first. And then finally on the right side, the derivative of sine of x is cosine of x. So the derivative of sine of y is cosine of y. And then we have to multiply by y prime. So you could think about it just like that, or you could literally put parentheses around it if you so desire. Not my fan, I'm going to write it like so. With that said, of course our challenge here is to actually attack x to the 5th y squared. So for our sake, I'm going to go through and do that in this kind of plum color instead. So we want to differentiate using the product rule. Looking in there, that means we're going to have the derivative with respect to x of x to the 5th times y squared plus x to the 5th times the derivative with respect to x of y squared. Now, although I'm not going to always write it this way, although I think I might on some of the problem sets solutions, although I'm not going to always write it this way, I think that writing this way the first couple times until you're comfortable with it is a really good idea, simply because you can quickly isolate when you're differentiating a y and when you're differentiating an x. Like, look at this guy. Here we're taking the derivative with respect to x of x to the 5th. That's clearly just 5x to the 4th. Although there's a y squared along for the ride, it wasn't actually differentiated in that part of the product rule, so we don't need to y prime at all. Contrast that, though, with the derivative on the right. Here we're differentiating y squared with respect to x, so our derivative is going to be 2y times y prime. In other words, because we took a derivative of a y function, in that portion, we actually had to multiply by y prime. So with that said, though, that was the product rule. We just kind of went down fairly smooth, I hope. We're left with 21y to the 6th y prime plus 5x to the 4th y squared plus 2x to the 5th y prime, and all of that is equal to cosine of y prime, or as I like to say sometimes, cozy y prime. So with that said, our next move is to get all the y primes on a single side. So a couple different ways to do that. I'm going to do this pretty quickly. So I'm going to leave the 5x to the 4th y squared on the left. Instead, I'm going to move everything else over to the right. And in fact, you'll start to see this move for me a lot in the problem set solutions. What I'm going to do is I'm going to pull out or subtract over all the stuff that has a y prime, these two terms, but I'm going to leave off the y primes and just do that GCF step in the context of the problem. So what I mean is I've got cosine of y minus 21y to the 6th minus 2x to the 5th y, and each of those has a y prime. So what I'm going to do is, since I moved them all to the same side, I'm going to factor out a GCF of y prime. So in a sense, I guess for the sake of color coordination, I should write that in green. Finally, our last move is to actually solve for y prime. And of course, that's just going to be dividing by this big old mess. So to make this simpler, I'm going to imagine doing that division and write it out as dy dx equals 5x to the 4th y squared. And it's all being divided by cosine of y minus 21y to the 6th minus 2x to the 5th y. And there is our derivative of y with respect to x in an implicit relationship. The big addition here was, once again, the product rule. So be on the lookout for those situations. There's definitely going to be a few. You should regularly expect them to be there. But again, don't panic. Just focus on which part you're using the product rule with and when you're differentiating an x and when you're differentiating a y. And you'll be able to take your way through it. Okay, finally, the last piece here is actually just to try it. I want to make sure that I finish this lesson pretty fast, and that's basically all the big stuff that's here. But I am going to challenge you to do your first work with the tangent line, as well as deal with a secondary wrinkle in this problem, pertaining to the information I gave you about the point of tangency. Now with that said, though, I want you to work through this one, and this might take a little bit, and I'm hoping there's enough time on this advocacy day for you to be able to work through it. But for the moment, please work your way through this problem and treat it as a try it. Try to find that equation of the tangent line, and you can do that by pausing the video. So, if you haven't already, please pause the video now. Okay, welcome back. Thanks for trying that try it, assuming you had time. Basically, in looking at this problem, I'm hoping that you found that, in truth, that the derivative itself was a fairly standard piece to find. You'd have to use the product rule, but not too bad. But that what made this difficult was the fact that I only told you that x was equal to 1 and our point of tangency was in quadrant 1, which meant you had to figure out some information about y from the equation. So to start with, ignore the plum-colored work up the top. Instead, I'd rather ask you to focus first on the derivative. So the big thing to check for, the thing that I'd hope everyone was able to get to, was the derivative right there in bold now. Negative quantity 1 plus 3x squared plus 6y over quantity 6 times x plus y. So if you got to here, consider it as you got 3/4 of the problem. You did the hardest, you did the important piece here. You know how to differentiate implicitly, and you were able to successfully do it even when the product rule popped its head in, or reared its ugly head. Now what made this one difficult was once you got there, you only knew that x was equal to 1 and that your point was in quadrant 1. So what that meant was we had to use that information to figure out what was true about y. What in the world is the y value? Because our derivative revolves around both x and y. So to get there, I took into account the fact that this equation that gives us our curve that we differentiated earlier in the problem is actually what the relationship is between x and y values. In other words, any point on this curve, including the point of tangency in this case, has to satisfy x cubed plus 6xy plus 3y squared plus x equals 26. So what I did was I took x equals 1 and I plugged in x equals 1 to that equation. Notice I've replaced x cubed with 1 cubed, 6x with 6 times 1, and x with 1. When I did, I was left with a polynomial, and in particular this polynomial is a quadratic in terms of y. And that quadratic in y actually factors to 3y plus 4, y minus 2. That means our y value, the only y values that satisfy this equation, are either negative 4 or 2. But since our point had to be in quadrant 1, that means that our y value had to be equal to 2, which means our point of tangency is actually x equals 1, y equals 2. And with that in place then, we're able to go back to the derivative and actually evaluate it at the point 1, 2. When we do, we end up with the derivative, or the slope, negative 8 over 9, and that means our equation, tangent line equation, why is it so hard to say that? Our tangent line equation is equal to y minus 2 equals negative 8 over 9 times the quantity x minus 1. So with that in place, again, pretty involved work to get to that point, but at the same time, I think this was a good challenge. It's a good one to talk about too if you're still confused. Maybe you can pause the video and go back and listen to that explanation up here. But this sort of task will be involved on your problem set tonight as well. There's going to be lots of opportunities for you to practice and kind of put it into action. But of course, there will be video solutions to help you. So, as a quick recap of everything we did here, as a reminder, we started out by pointing out that there are other relations out there than just the explicitly defined y equals f of x ones we've seen before. Sometimes, like Nathan in his iClub Baby Steele shirt, you have to do a little bit of extra work with an implication in a relationship. So from there, the next thing that we did is we looked at differentiation in general and emphasized the fact that we can differentiate a lot of relations, even those with all sorts of variable scalars, because of the fact that we know we're differentiating with respect to x, and we're seeking that slope expression dy dx. With that in mind, we went through and we figured out that when we differentiate something like this circle, there's an issue that comes up with differentiating a y expression in terms of x. So what we did is we used the chain rule. The chain rule was our key, and when we did, we were able to create an expression that back substituted as 2y prime, or 2y dy dx. With that in mind, all we had to do to solve for the slope was solve for y prime, which was just a matter of doing a little bit of algebra. After that, we did a quick little excursion to point out that explicit differentiation does accomplish the same thing for situations when it's possible to solve for y explicitly. Sometimes it just looks a little bit different, like in this situation where we had a plus or minus square root that stuck around in our equation. Still, we got the exact same slope relationship that we had before. Beyond that, we did a couple derivative examples working through our plan with a very basic problem, and then we did a try it to check our ability with that basic skill, before moving on and seeing how the product rule might pop in. Now again, we only did examples with the product rule, but of course we could have had the quotient rule as well, and in fact tomorrow we'll see a little bit more quotient rule, as well as of course the possibility of a chain rule within an implicit problem, something like the derivative of sine of y squared, which again we'll hit later. After that, I gave you one more try it, where you had the opportunity to write the equation of a tangent line using implicit differentiation, but with the added caveat that you had to actually use some information about the original function to find a particular value of y. So, and that could work with y or x depending on the problem. So with that said, that does complete our work for the lesson today. Hopefully this has been just fast enough for you to have time to work through it all in class on an advocacy day or a potential advocacy day. But in any event, hopefully you'll feel supported here as well as with the video solutions. And again, I wish I was there with you guys teaching you this in person and making lots of fun illustrations like this one. But until I can come back, hope this has been helpful. Happy learning and have a great day.